Dalton's law of partial pressure tells us that the total pressure that is in a gas container is the sum of the partial pressures of each of the gases that are present. So we can say that the pressure total is equal to the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3, etc., however many gases you have. It doesn't matter what type of gas is present. Again, why not? Because gases are mostly empty space. The size of the individual gas molecules doesn't matter. It doesn't matter if we have helium or xenon. The gas particles don't touch, and the gas volume is dependent upon the pressure and the temperature and the amount of gas present. So if we add up the pressure of each gas in an individual container and we put them all into the same container, the pressures add up. The example I show here, I have a blue gas, and you can see there's not many gas particles present. It doesn't have a very large pressure. The green gas has more gas particles present. It has a little bit higher pressure. The red gas has the most particles. The pressure is the highest. If I put them all into the same size container, the pressures are additive. The total pressure is equal to the pressures of each individual gas added up. Another way to look at that, let's talk about moles of gas. If I have 0.6 moles of H2, it exerts a certain pressure. And the picture here says that the pressure that exerts is 2.9 atm. In another container, same size, I have 1.5 moles of helium. More moles, higher pressure. The helium exerts 7.2 atm. If I put both the hydrogen and the helium in the same container, you can see we have many more gas particles, and the pressure increases. The pressure total is equal to the two pressures of the two gases that are present. How would you work a calculation? If you knew the moles of one gas with the temperature and the volume, you could get the pressure of that. You calculate the pressure of the second one the same way. You add them together. To get the pressure of each, add them, you get the total pressure. Another way, add the total moles together with the volume and the temperature, you could get the total pressure. Another way that we measure gas concentration is mole fraction. We've done the mole fraction before, and now we're going to do it again. The mole fraction is the moles of a substance over the total moles present in the mixture. So if I have a gas mixture of hydrogen and helium together, the mole fraction of hydrogen is the number of moles of hydrogen over the total moles, the moles of hydrogen and helium added together. The mole fraction is related to the partial pressure. Mole fraction is a strange little X that looks like this. So the mole fraction of a gas is equal to the moles of that gas over the total moles present in the container. The partial pressure of the gas divided by the total pressure of the gas is directly related to the moles. The pressure exerted is directly related to the moles. So we can use the relationship that the mole fraction is equal to either the moles over the total moles or the partial pressure over the total pressure. It's a pretty nifty relationship. So let's work a sample problem. A mixture of 10 grams each of hydrogen gas, oxygen gas, and water are present in a 10-liter container. Calculate the partial pressure of each gas, the total pressure in the container, the mole fraction of each gas. Assume the temperature is 25 degrees C, which is 298, and the volume is 10 liters. There are a lot of different ways that you can use to solve this problem. I think that I'm going to first figure out the moles of each gas, and then I'm going to use the ideal gas law to get the pressure of each gas, and then I'm going to add them together to get the total pressure. And then to get the mole fraction, I'll just divide either the moles of each by the total moles, or I could divide the pressure of each by the total pressure. Either way will work. Let's figure out moles first. So I have 10 grams of hydrogen. Remember, hydrogen is diatomic, 2.02 grams per mole. So I have 4.95 moles of hydrogen. For the oxygen, I also had 10 grams. O2, also diatomic. I have a lot fewer moles of oxygen because oxygen has so much higher of a molar mass. So the partial pressure of oxygen is going to be much lower than that of hydrogen. And then for the water, the molar mass is between the two, so I'm sure the moles will be between the two. It's 18.02 grams per mole. So my moles of water vapor are 0.555. If you wanted to add that up, you would have 5.818 moles total, if you wanted to get the mole fraction using the moles over the total moles. Now I'm going to get the pressure. I know that PV equals nRT, so my pressure is going to be nRT over V. So for the first one, my pressure of hydrogen is going to equal 4.95, 0.08206. My temperature was 298, and my volume is 10. So my pressure of hydrogen gas is 12.1 atm. For the oxygen, the pressure of oxygen, we'll set it up the same way, 0.313, 0.08206, 298. You'll notice that I'm not using my units, but I know that they're the correct units. So my pressure ends up in atm. So this is 0.765 atm. And then finally, my pressure for the water vapor is equal 0.555, 0.08206, 298, again divided by 10. So my pressure of the water vapor is 1.36 atm. My total pressure, I can just add that up, and I get 14.2 atm. And then for the mole fraction of each, if I have the mole fraction of H2, that equals 4.95 over 5.82. It also equals 12.1 over 14.2. I can either use my mole over total mole or pressure over total pressure, and I get my mole fraction of H2 is 0.852. My mole fraction of O2, I'll just use the pressure this time, 0.765 over 14.2. So my mole fraction of O2 is 0.0539. And then finally, my mole fraction of the water is 1.36 over 14.2. And that equals 0.0958. Mole fractions always add up to 1. Recall percent composition adds up to 100. Mole fraction adds up to 1. And if I add together my hydrogen and my oxygen and my water, you'll find that the total is 1. So I used the amount of each gas to go to moles, the ideal gas law to use pressure, and then I divided the pressure of each by the total pressure to give my mole fraction, or the moles of each by the total moles to get the mole fraction as well.